All right, gentle people, let's go ahead and tackle this problem out. The first thing we want to know is the equilibrium pressures giving a starting amount. And so that means we're going to go ahead and invoke an ice table. So let's go ahead and write the reaction that we're interested in. So here's our reaction, and I want to make a real big point about writing the states of our reactants and products because it's going to make a big difference in this problem. So I'm going to go ahead and write ICE down the side. And what you'll notice is I have solid reactants and products in this chemical reaction. And remember, solids are not part of my equilibrium constant. What that means is they do not matter in the context of our ice table. So I'm just going to put happy faces down the solids because they are not going to matter in this table. Now, in this problem, I start out with 0 CO2. I'm going to have a change, and I'm going to make CO2 as my calcium carbonate decomposes. The equilibrium pressure of CO2 is simply going to be X. So now what I can do is I can use the Kp that they provided. Now Kp is going to equal my products, so that's the pressure of CO2. But remember, a solid is going to be inputted as unity or 1. It doesn't have a pressure, and so we don't have to go ahead and consider it in the context of Kp. I'm going to divide this by my reactants, but my reactant is just a solid, so it gets 1 for its inputted value. So what this means is that Kp equals the pressure of CO2 at equilibrium. Now we know that the pressure of CO2 at equilibrium equals X, and we also know that Kp equals 1.16. What this tells us is that the pressure of CO2 at equilibrium is 1.16 atms. Now ultimately in this problem, what we want to know is the amount of calcium carbonate that decomposed to produce this pressure. So what we did is we found out information about a product and we want to relate it back to a reactant. What that means is we should convert our information into moles. To do that, we're going to use the ideal gas law. So PV equals nRT. So PV divided by RT is going to get me moles. So let's plug in our values. So our pressure is 1.16. The volume of this container is 10 liters. My gas constant, I can look up on my constant sheet, and we should input our temperature in Kelvin. So they gave it to us as 800 degrees Celsius, and so I'm just going to go ahead and add 273 to that. I can run this calculation out, and I see that this is 0.1317 moles of CO2. Now, based on our equation, you guys can see that CO2 and calcium carbonate are in a 1-to-1 ratio. So that means to produce this amount of carbon dioxide, I had to go ahead and consume or decompose 0.1317 moles of calcium carbonate. So this is the amount that is consumed. Now in this problem, I want a mass percent of the amount consumed. And I want my mass percent in terms of grams. So let's go ahead and convert our moles to grams. And to do that, what we're going to do is we're going to times it by the formula weight. So we're going to look up on our periodic table what each of these atoms weigh. And if we do this calculation out, it turns out this amount of moles is 13.18 grams of calcium carbonate. So the last thing we have to do is we take the amount that I consumed and divide it by my starting amount, which was 20 grams. I'm going to times this by 100%, and what I get out is 65.9% of my original sample was decomposed to give me this equilibrium pressure. I hope that made sense.